Okay, level 2. And this would be number 6. Nope, sorry, not number 6. This will be number 3. Number 3. And number 3 says, if you could jump with an initial speed of 5 meters per second, how many jumps would you need to go up to the top of a 50-meter high hill? Okay, so here's you when you jump. You jump up and you fall back down, right? That's how a jump works. And when we do a jump, we have to realize what happens to our speed. We initially start off by jumping with a high speed, but as we get up to the top, as we approach the top of our jump, we're slowing down, slowing down, slowing down, slowing down, slowing down, until up here at the top, our V2 is 0, right? And then we start speeding up, speeding up, speeding up until we get back down here, and our speed, I'll call it V3 at this point, is actually fast again. In fact, V3 and V1 are the same magnitude, they're just one's up and one's down. And at the top, we have this speed of 0. So this is interesting because we can now use a very easy comparison of the kinetic and potential energy. When you jump, you start with EK, right? So I'm going to redraw this picture just looking at the energy. So here's the picture, here's the jump. Right here, you start with a lot of EK because you have speed. Remember, 1/2 mv squared. But you're losing that speed as you go up. So at the top, you have EG because you've gained height. You've gained height, but you've lost your speed. And then as you go back down again, you have lost your height and gained your speed. So what we see here is a beginning energy of kinetic energy, which changes to potential energy as you trade your speed, which drops to 0, for your height, which increases. And then that same gravitational energy decreases as you fall down, losing that height, but gaining speed again. So what we can do is use this and use the conservation between the top and the bottom, the conservation of energy. Let's put the EK here and the EG up here. All right. So we write this statement: the total energy in position 1 is the same as the total energy in position 2. The law of conservation energy tells us that you can't lose energy. It has to be accounted for. Okay. So if we look at position 1, which I'll put in red, that's down here. There is no height. So essentially, when you write this equation, you can have that. What this means is you take the total kinetic energy of position 1 plus the total gravitational energy of position 1, and then you do the same thing for position 2, and those numbers have to be the same. But we only have EK at position 1. There is no height in this case, so there's no EG1. And in position 2, our speed is dropped to 0 at the top of our jump, and so there is no EK2. So this simplifies to EK1 equals the EG at position 2. And then 1/2 mv1 squared equals mg and the height at position 2. And then we can put in we can cancel out the m because it's on both sides of the equation. So then we have 1/2, and it says that we can jump with a speed of 5 meters per second. So let's put that in as our initial speed, and then over here, 9.8 h2. And if we do the math here, if you crunch this out, you've got 25, right, divided by 2, which you're going to have 12.5 equals 9.8 h2. And then if you divide both sides by 9.8, you're going to get 1.3-ish meters. So what does that mean? What is h2? Well, if you look at what we drew, it's the height you would get to when you jumped. So that's the height of your jump. h2 is the height of a jump. So you use the speed of jumping to figure out what the height of the jump would be by looking at the change in the energy from kinetic to gravitational. Now that you know the height of one jump, which is 1.3, you have to get to 50 meters, so you can simply figure out how many jumps. N jumps. I'll put N. You'll figure out the number. 50 divided by 1.3 means looks like about 38 jumps. Because you can jump 1.3 meters each jump. Okay? So again, whenever you see jumping, think about how a jump works and think about the change in energy and use the conservation of energy equation to figure out either the h or the